Okay, hi everyone. This is Screencast is about finding the area bounded by a polar curve. All right. So the first thing I want you to do here is take a look at this dimpled limaçon, and I will share with you that if my classes at the end of the day today were any indication, I think everyone is like they're all there. I feel like everyone is kind of like cooked potatoes, just struggling to drag their mush across the finish line that is the 2018 calendar year. We're just all dying. They're dying. All right, here's what I want you to do. For this dimpled limaçon, would you go and take a highlighter and highlight the portion of the graph that is traced over the interval of theta from, let's say pi over 6 to 2 pi over 3, and then replay me. So if you were highlighting this, my guess is you probably asked yourself, well, when theta equals pi over 6, okay, here is pi over 6. When theta equals pi over 6, I'm right here. And when theta equals 2 pi over 3, I am right here. So the portion of the graph that is traced over that interval is right here, okay? And I'm going to do this also right down here. This is at theta equals pi over 6, and this is theta equals 2 pi over 3. And now here's what I want you to write down in a minute. When we talk about the area bounded by the polar curve over the interval of theta from pi over 6 to 2 pi over 3, okay, so that phrasing is really important. When we talk about the area bounded by the polar curve, r equals 3 plus 2 cos theta over a specific interval of theta, it's important that you even know what area they're talking about before we start going into the calculus of this, okay? When you see this phrase, the area bounded by this polar curve over an interval of theta, let me make sure you know what the area that is. That is this area right here. It is the area bounded by the polar curve and the radial line, so to speak. So unlike the area bounded before, the area bounded, we're talking about a curve defined in polar coordinates, the area bounded here is kind of the area as theta kind of rotates around, all right? So the area ends up being kind of a wedge shape as opposed to, in functions of x, the area is with respect to the x-axis. Here's a phrase that's going to be odd for you. The area in a polar curve is the area bounded with respect to the origin as the radial line rotates through the interval in question, okay? So this area in blue is what we're talking about. Now, I'm going to talk to you about how to describe this area using a definite integral. And before I just give it to you, and I know you just want to see what the result is, what I want to do here is just kind of tease you along for a minute. If we think about dividing this interval into subintervals, now remember, with functions of x, those subintervals were rectangles, weren't they? Well, in here, in the polar world, the subintervals are not changes in x, they're subintervals over small changes in theta or d theta, okay? And maybe you can appreciate kind of where we're going with this, but these subintervals are the subintervals over small changes in theta over the larger interval in question of theta equals pi over 6 to theta equals 2 pi over 3. If you are curious about how this relates to a limit of a Riemann sum and how we, at the end of the day, derive how we find the area of a polar curve, I'm going to do that right after I show you what the integral expression is. But this shaded area here, so in general, well, let's do the specific first. The area bounded by R over this interval of theta is given by this integral expression. The definite integral from pi over 6 to 2 pi over 3 of r squared over 2, and what's the dummy? The dummy is d theta, because r is a function of theta. What I almost always do is I pull the 1/2 out, 1/2 pi over 6 to 2 pi over 3, r 3 plus 2 cos theta squared d theta. Hello? In general, when you have these polar integral, polar area questions, more often than not, when you try to evaluate this integral longhand, you're going to have to use cosine double angle. I'll show you the algebra tomorrow. But for tonight's homework, what I'm asking you to do is just generate the integral expression to describe the area. In general, when you talk about a polar curve, the area bounded by r equals f of theta over the interval of theta, and we'll just call it theta 1 to theta 2. This is described by the definite integral, the following. It's 1/2 the definite integral from theta 1 to theta 2 of r squared d theta. Okay, now I'm going to talk about why it works at the very end of this. So those of you who don't necessarily care to see where this area integral comes from, you certainly don't have to watch it. I will say that when you watch a derivation, it gives you I think a better and more comprehensive understanding of what the calculus can do, and then what you can kind of work through when you have questions that are sometimes out of the box. So that's kind of my subtle way of saying I think you should watch it, the derivation. But before I get to that, I'd like you to do this, okay? Let's let this be the case. R equals 3 sine of 3 theta. And I would like you to generate 2 different integral expressions, so 2 different integral expressions that would describe the area of one of these petals. So I want you to describe the area of one petal using 2 different integral expressions, and then replay me for the answer. Okay, what I did here was I just did a quick sketch of this rose. I made a note of the fact, if you look at the orange, that the rose starts right here, and then it heads in this direction. And at pi over 6, I'm at 1 petal length extension, which tells me then that in 30 degrees, 1 complete petal is traversed. So the area of 1 petal, here you see me going from 0 to pi over 3 of 1/2 r squared d theta. And I just chose a second expression. I just doubled the integral over 0 to pi over 6. Hi, honey, how are you? So either of these are fine, okay? And obviously you could simplify 2 times 1/2, all right? So now you see why yesterday, I don't remember who asked. I think it was Walter. Maybe it was Arjun. Maybe it was, I don't remember. But it is far to your advantage to be able to sketch these polar curves quickly, knowing where you are at what value for theta, so you can make the calculus work in your favor. And just so we're clear, in both cases, I described the area of this petal right here, okay? If you wanted to, and if you were feeling particularly, wild, you could go ahead and describe the area of this green petal. And in fact, why don't you try and tell me what the interval of theta is over which this theta, that petal is traversed, and then we can answer that question in a moment. If you want to answer it on your own, then replay me. But that green petal is traced out over the interval of where, everyone? Yes, pi over 3 to where? Well, what do you think? Pi over 3 to 2 pi over 3. Okay? All right. That is it for this screencast. As far as new content goes, I'm going to go right now and derive this for you, okay? When you're talking about a polar curve. And I'm just going to draw a dimpled limacon here for ease. All right. When you're talking about a polar curve, what you're doing when you ask yourself, what is the area bounded over some interval from alpha to beta? And when you acknowledge the fact that you're talking about this region, you have to ask yourself this question, just like we asked ourselves back in the day of functions of x. If we looked at very, very, very small subintervals here, the subintervals are going to be these kind of triangular slices, right? They're no longer rectangles. These are the subintervals. And if you look at this, each subinterval is an infinitely small sector. So I'm going to zero in here on this kth subinterval, if you will, okay? This kth subinterval right here. And the kth subinterval, if you were to zoom in smaller and smaller and smaller, you'd find that each pi slice, if you will, approaches the area of a sector of a circle because, and here's where you're going to have to be a little bit flexible with me. If I take a look at the bounding radial segments of this sector, okay? The bounding radial segments of this sector as change in theta, as d theta approaches 0, would you agree that these two radial sector segments, they approach each other? Okay, so if the two radial segments approach each other in length, then this sector you could really conceive of as a sector of a circle, okay, if you will. We're being a little bit kind of loose just to see if we can see where the integral expression comes from. So the area of a sector okay, the area of a sector of a circle is given as the central angle, and just like we talked about over here, this central angle, it's a really, really, really small change in theta. The area of a sector is d theta all over 2 pi because it's a fraction of the area of a circle. And once again, when you zoom into any polar curve, if you zoom into a small enough change in theta, what this segment approaches is the area of a circle. So the area of a circle is d theta over 2 pi. This gives you a fraction of the circle times pi r squared. That's the area of a circle. And if you look at this, if I'm in radians, because look at the small theta over 2 pi radians, only if you're in radians does this nicely happen for us. The pi's cancel, and we're left with then 1/2 r squared d theta. That's the area of one of these sectors. And when you want to add up infinite sectors, what we get here is, if you want to add up the sum of infinitely small sector areas over an interval of theta from alpha to beta, for example, you know where we're heading. Whenever you're adding up the sum of infinitely small somethings, you know we have a definite integral. That is, this is my integrand, the definite integral from alpha to beta of 1/2 r squared d theta. What is that? No one knows. 1/2 r squared d theta, which becomes just 1/2 the integral alpha to beta r squared d theta. Okay, hopefully that made you not unhappy. I will see you tomorrow, my crazy calculus class. Goodbye.